This is Lecture 9H on the equations of population dynamics for Calculus 2. In this lecture, I'll first run through several models, each of increasing complexity for population dynamics, and then go back and solve the first two. The later ones are more complicated and can be solved only by numerical methods. Okay, the most elementary, so we start with the most elementary method, which is this one right here. It says the rate of change of the population is proportional to the size of the population itself. So if you have a population of 2 individuals, it's going to grow slower than a population of 2,000 individuals. That's all this says, and it sort of makes intuitive sense until you look at the solutions. What k is, this constant, is the difference between the birth and death rates. So if k is greater than 0, then the death rate exceeds the birth rate, and this population decreases to 0. That's expected behavior. If k is greater than 0, that means the birth rate exceeds the death rate, then the population will increase without bound. And this is highly unrealistic. So the next model addresses this problem with the unlimited growth. Now here's the second population model, and there's an added term. We're not going to derive this model, how this model came about. We're just going to use it. Okay, this model adds an m, which is the carrying capacity of the environment. This is the maximum population that the environment can support. So if you're growing a bunch of bacteria in a petri dish, and the population will increase to the point where they have no more oxygen, room, food, whatever. They can't grow any further. That environment limits the maximum population. And the equation for this is the logistics equation. And it appears not just in population dynamics, but in other fields as well. And its solution, appropriately enough, is called the logistics function. Now the third model adds another term called the minimum viable population. So the idea is that if you have a real small group of anything, say a small group of some kind of animals, you can't expect that over time this population will grow. In fact, it might just die out. So you have the rate of change of the population depending on how big the population is itself, on this carrying capacity of the environment, and the minimum viable population. So you see, this is getting more and more complicated, but more and more realistic as well. These next two models I'm mentioning just for completeness. I'm trying to give you a little catalog here of these different models of population growth, population dynamics, so you can use it for a reference. You'll see these equations elsewhere with sometimes very confusing and overlapping notation. I've tried to be consistent here. Okay, so the next thing you add are the next refinement to the population model. Here I haven't included the minimum viable population, but the carrying capacity is still included here. But you include two other terms, and they have to do with how individuals enter and leave the group. Now, if you don't have these other terms, the only way individuals enter or leave the population is by being born into it or by dying. But of course, you can enter or leave in different ways. And so we have another term, which I'm calling S, and that's a rate of decrease. So you can leave because you got hunted, fished, harvested, or you emigrated out. And there's another term. You see this is negative, right, because it's a decrease. And then you have another term, A, and that's the increase. Population can increase from immigration from other populations, or perhaps if you work for Fish and Game, by stocking. All right. Now the last refinement I'm going to talk about here is one that would include temporal variations. Okay, the population of fish in Casilla River varies with the time of year. And so that could be included. So temporal variation could be included. Okay. So now those are just kind of showing you the increasing complexity and increasing realism of the population model. And now we're going to go back and solve the first two models because we can do that analytically in this class.